All right, today we're going to take a look at Chapter 14. And Chapter 14 is a branch of mathematics that you may not have seen before, and it's called graph theory. There are like up to graduate level courses in graph theory, but the things that we're doing are not necessarily complicated parts of that. They're the real base level stuff. It's not things that you can't handle, but it just means that they're things you probably haven't seen before. So some terminology, some pieces of information, and we're just going to get started. To start with, we're going to be talking about things called graphs. Graphs are simply a collection of vertices, at least one, and edges. And each edge connects one vertex to another. So the picture that you should have in mind, let me get this, would look something like this. It's a bunch of dots, okay? And make my dots look like my paper. Put one over here. And there's segments that connect them. So you have things that look like this, and maybe like this, and maybe like that. Hang on, that doesn't look great. Let's try that. Okay. This would be considered a graph. There are some conditions upon which we're going to build our idea of graphs. The first one is, get out of your head right now the idea that those segments have to be straight. I very much easily, although it would have been messier, could have drawn this so that it looked like this. It doesn't matter whether they're straight or not. They could have curvature to them, not a big deal. I tend to draw them straight because it's easier to draw them straight, just in terms of connecting points, but it doesn't matter. The graphs that we're working with are all going to be called simple graphs. So a simple graph is a graph in which there is no more than one edge between vertices and no edge from a vertex to itself. So in particular, what is it excluding from happening? Well, it's excluding from happening something like this. Oh my goodness, I can't draw. Let's try one more time. There's two edges between these two vertices. That's not going to happen. So this is a no. We're not going to do this. We're also not going to have a point that has an edge connecting itself back to itself. Sort of a circular edge kind of thing. Okay, so that's not going to be considered appropriate or correct for any of the graphs that we're doing, because all of our graphs, like the note here says, are going to be simple graphs. So we're not going to have anything like that going on. It is worth noting that there's something else that can happen back in this sort of original first sketch of a graph that I did. We could have a graph where it looks like that we're overlaying the edges on top of themselves, but there's no point there's no point right there in the middle where it looks like they're crossing. So you can have a couple ideas in mind regarding this. One is that I didn't have to draw it like that in this particular scenario. I could have drawn it like that, right? I could have done that. Or another possibility that you can have in your mind is something like what happens with roadway construction. So at this point, we have this going on somewhat downtown Oklahoma City area. But if you think of larger cities, you see this happening a lot. So think like Dallas or Chicago, where the roads are on top of one another, like vertically. And if you were to look down from on top to the bottom, it looks like they're crossing, but they're not because you're in free space, right? So have that kind of picture in mind. Just because it looks like it's crossing, if there's not a dot there, then they're not actually crossing there. There's not a vertex there. Good? Okay. So we're just going to take a real basic graph. This is the one that's drawn for us. And we're going to determine how many vertices and how many edges that the graph has. We're just counting things. So if you were to count here, how many vertices do you have? Yeah, there's 7. And how many edges do you have? 7. These are not always the same value. They don't have to be. They just happened to be in this graph. Right? Okay. Each of our vertices have a certain number of edges that sort of connect to them. Right? So if I'm looking here at D, D has two edges that are kind of connected to that vertice, right? We actually call that the degree of the vertice. So So the degree of the vertex is just the number of edges that join to that vertex. And you're all on the same screen. I'm going to copy mine over. I promise I'll come back just a sec. But using this same picture here, we're going to identify the degree of each of our points. So I have A, B, C, D, E, F, and G. That's not drawn well. That should say G at the bottom. Does yours say G? Yeah. Okay. Mine does not. Typo there already. Okay. It's going to happen today. All right. So A, how many how many edges are at the vertex A? 2. How about B? 2. C? Just 1. D? 2. How about E? Yeah, there's actually 3 at E. F? 3. And G? 1. Okay, we're going to see a theorem in just a moment that talks about what happens when we add these values together. But let's just notice what we think it might be right now. If you were to add 2, 2, 1, 2, 3, 3, and 1, do it real quick, you get the sum of 14. So it kind of feels like that the sum might have some connection to either the number of edges, which was 7, or the number of vertices, which was 7, right? Feels like it might be double something. And it is, and we'll talk about what it's double in a little bit later. But that's not happening by accident. That will always happen. And it's actually doubling. Which one do you think? Do you think it's doubling the edges or the vertices?
The vertices?
It is. It's doubling the vertices. We'll talk about why in a little bit. Okay. Let's take a look in a minute for a couple more things, details. Isomorphic. Have you ever heard that word before? It's a really good math word, isomorphic. Okay. Isomorphic graphs are 2 graphs such that there is a 1-to-1 matching between the vertices of 2 graphs with the property that if there's an edge between 2 vertices in the one, there's an edge between 2 vertices in the other. Conceptually, isomorphic really means it's just a rearrangement of something. If I were to rearrange it in some way, it'd be the exact same thing I already had. It's not really any different. That's what isomorphic means. It's not really any different. It's actually on the next screen, I think. Sorry. Yeah, it's on the next screen. So you have an example on the next part of your notes. It looks like this, roughly speaking. Yeah? Awesome. And what it wants us to do in the notes or in the directions of this example are to determine whether the graphs are isomorphic. Is it really the same graph? Because I'm telling you what, it doesn't look the same, does it? It doesn't. It doesn't look the same. And we need to figure out if, in fact, maybe it is. And so we're going to take a look, and I can't remember. I wrote them in. I don't think I really wanted the letters written in there. The letters actually work like it is. In general, they won't give you the A, B, C, D the way that this was drawn in here. It would have, for example, just the pictures here without the vertices. And we would want to decide if in fact it's isomorphic. So don't erase yours because they're correct. But let me actually start with where it actually should have started, which was right here. So we've got these labeled vertices in the first graph. And what we want to do is we want to make a pairing of the dots here to the dots over here and see if it actually works. Now, a real quick check to see if it's going to be isomorphic, at least it would rule it out as a possibility potentially, is do they have the same number of vertices? They do. If they don't, you're already out of luck. You're done. Do they have the same number of edges? They do. Yeah, so just checking those two things at the beginning will save you some time. If it's going to, I mean, if it fails one of those, you're going to fail everything else afterwards. You might as well fail it fast, right? Move on. All right, so if we have the same number of vertices and edges, it makes sense to try to move ahead and make a mapping that makes them isomorphic. So what we want to take a look at or shows that it's isomorphic is, we'll just start with point A just because it's alphabetical. What's the degree of point A? 2. The degree is 2. So we're going to find one of the locations in the other graph that also has a degree of 2. And in particular, the one that's listed on your paper, and a nice one to choose, is that top one. But I could equivalently make it the bottom one, and it would be okay, right? Okay. There's another point, namely D over here, that also has a degree of 2. So that means that it has to be the location at the bottom because it's the only other point with degree 2. Make sense? So that's how those are getting connected to those two locations. There are only 2 other locations, but it is a good idea to notice that B and C both have degree 3, right? So I don't necessarily know that it has to be a B here and a C here, but we can put them there, and if it doesn't work, we could switch them to test it as well. So the part you have written down has a B here and it has a C here. So this is my guess as an isomorphism that connects one graph to the other one. And I can check to make sure it really works by connecting the points. So I'm going to use some colors to do this. And I wanted to bring you some colors. If you have some colors with you, it will be helpful to grab them out. If you don't, just go back later and do the coloring so you can see it, okay? So here's what this looks like. A is connected to B, and I'm going to use an orange line to do that. I'm going to take it a little bit thicker. A is connected to B here. So in order for it to be an isomorphism, A has to be connected to the B over here as well. And it is. Right? If somebody near you has colors and you could share, that'd be amazing. I have 3 colors up here, actually, if anybody wants them. I have purple, green, and orange. Does anybody want some purple, green, and orange? No. Okay. All right. It doesn't matter where we go next. I'm just going to keep going around. The B is connected to the C, so we're going to change colors. I'll use pink. B is connected to C over here, which means B has to be connected to C over here. Is it? It is. It's in the middle. All right, so back in my original graph, changing colors, we'll use blue. C is connected to D. So is C connected to D over here? It is. C is connected to D. We'll change, let's go with red. B and D are connected. Are B and D connected on the graph that I've got over there, the second graph? Yep. And the last connection, we'll go green. I have A connected to C. That's the A connected to C over here. So I'm trying to see if I can do some kind of a connection like this. And if I fail, I didn't fail here, right? It worked. If I fail, it means I need to go back and figure out, did I make a decision that could have been reversed? In this point, in this particular problem, there's 2 decisions that I made that could have been reversed. A and D could be in different locations, right? Those could have flipped. Or the B and the C could have flipped. Those are the only places where I had decisions. And in this case, kind of didn't matter because the graph has these beautiful symmetries going on, so it seems reasonable that it shouldn't matter which one I did. But in some graphs, there's not a lot of symmetry going on, and I do have to make some legitimate decisions about where I put my locations and my points. Okay, does that make sense? So these are isomorphic. Change my color back. So it says determine whether the 2 graphs are isomorphic. The answer is that yes, they are. And it says if so, label the vertices, which I accidentally inadvertently did on the paper for you. Sorry about that. They're labeled so that they actually work, and then we color-coded them to show that it did. Okay? So I'll be real honest, I'm not exactly sure how this shows up in my math lab. My guess is that it shows up with multiple choice, and you pick which one works. And there's probably an option that says none of the above. That's how I'm suspecting that it will show up. You can let me know if I'm right or not next class period, but that's what I think it'll look like. Because it doesn't have a good way for you to draw it in on yourself, right? Draw it in yourself. It's not a thing. All right, next description of a graph is a connected graph. A connected graph is a graph where we can move from each vertex of the graph to every other vertex along the edges of the graph. So in other words, I can get there. And clearly a disconnected graph is the opposite. It's a graph in which we can't do that. So as we're thinking about graph theory, I'd kind of like you to think about the campus. Imagine all the locations on the campus, the buildings, let's say, as vertices, and the sidewalks as our edges. Now, there's sidewalks that get you directly from one place to the other, and sometimes that doesn't fit with this simple graph idea, right? There might be two different sidewalks you could take to get from this building to another building. I understand that. But if we eliminated those kinds of an idea, it fits pretty well with the idea of a connected graph. Nowhere on campus are you forced to walk across the grass to get somewhere. That doesn't mean you might not walk across the grass to get somewhere. In fact, you've probably done it, right? But there is a sidewalk that you could have used. It would be in the idea of a connected graph. Those sidewalks form those connections. Now, for the most part, like when Google Maps or MapQuest or whatever the mapping programs are that you have do this, this is what they do too, right? But then they do weird things. When we went skiing last year, I may have already told you this, when we went skiing last year, I reserved a location for us to stay. It said on Airbnb or Vrbo or whatever I was using that it was just 30 minutes, or it said it was 20 miles, I think is how it said, 20 miles from the ski slope we were supposed to ski at. We got to about 2 weeks before the event, and I found out that it tried to do my mileage straight over a mountain range. This is a problem. We were an hour and a half away from the ski slope, the location that I made my hotel reservation at. That's not good, right? That is a flaw in their program. It's a graph theory problem is what it really is. They did it as the crow flies. I mean, like, I can't fly from my location to the ski slope. This is a problem, okay? So when we're looking at this, we're talking about connecting them via some sort of reasonable, roadway. We're talking about sidewalk or something like that. So taking a look at this graph, is this graph connected or is it disconnected? If I take, there's some missing dots. Let me get my dots in there. There should be dots. I'm missing dots on my picture. I don't think they're missing on yours. I think they're in yours. All right, so using this picture, is it connected? Can I start at one dot and get to any and every other dot? No, I cannot. It's overlaid like on top of each other, right? But I would actually have to get off of the edges in order to get from, say, the point over here on the far left to the point over here in the bottom right. There's no edges that connect those two together. So this graph is disconnected. And while I haven't defined what I mean by the connected or the components, I bet you have a pretty good idea of what I should be meaning by components. The components are the pieces inside of this overall graph that are connected. Do you see how many components we have? What do you think? 3. Yeah, it's 3. Why is it 3, Jonathan?
Because you have the triangle and the end and the line that connects them.
Yeah. So there's a triangle over here on the left. You have this sort of random arbitrary line that looks like it's in the middle causing like an H or something. And then you have the piece over here on the far right that looks like the M. And those 3 pieces are overlaid on top of each other, but they're not connected, right? There's no dots. Now, if I put some dots here where these seem to be crossing, they would be connected, but they're not. I don't have dots there. Again, imagine like the overlaying of highways, right? So yeah, this has 3 components. And here, let me do this actually, just for the sake of it being in your notes this way. Let's try one more time. When I manipulate my graphs, I like to make a copy of them down here so I don't have to redraw them later. Okay, so if I were to do the same kind of thing I did on the previous screens with colors, I could mark that this is one graph that's one piece of the graph that's connected. This is one piece that's connected, and then we've got this piece that's connected, right? The 3 different pieces. So if colors would help you to identify these later as you're drawing them, please feel free to use those. All right, I mentioned this before. Sum of the degrees. This is a theorem. It says that in a graph, the sum of the degrees of the vertices equals twice the sum of the edges. We had to guess. Vertices, edges, which one should I be doubling? Remember my first graph? And I said, let's think about it. And we're trying to decide, is it the vertices or is it the edges? It's the edges. So let's think about why it would be the edges. Okay, so in this graph, we're just going to draw a very simple graph right here. The first point has degree 1, the second has degree 2, and the third has degree 1, right? This is the degree of each of those points. Let me make that look white instead, easier to see. Okay, so the sum would be what? Yep, the sum is 4. And you notice how many edges do I have? 2 edges. So you can see the doubling feature. I have 3 vertices on this one, so in this particular scenario, I don't have to question which one it should be, but let's talk about why it's doubling the number of the edges. Well, when I have my edges, every time I have an edge, it has to connect 2 vertices, right? Which means the edge gets counted over here in the first piece, and it gets double counted when I count the second piece. We've talked about double counting before, right? Here's another example of double counting. The edge gets counted twice because it gets counted in the vertex or the degree when I count the first degree of the first vertex, and it gets counted when I count the degree of the second vertex. And this happens for every single edge. So that's why this is happening. The second, or this example, example 5, talks about using this theorem without drawing a graph. You don't need a graph to do this. They're giving you the details without the graph. And we're trying to figure out how many of the edges there are. So we're deciding the number of edges that are in our graph. So it tells us we have a graph with 8 vertices. It tells us 2 of the vertices have degree 1, 3 of the vertices have degree 2, 1 of the vertices have degree 3, and 1 has degree 5 and 1 has degree 6. So it tells us the number of degrees of all the vertices. So like you could draw a graph that does this if you wished. You could actually draw it. I mean, it says you don't need to do it, but you could if that's what you wanted to do. But according to the sum theorem above, all I really need to know is the sum of all of these degrees, and then I can backtrack and I can figure out how many edges would have created a graph that resulted in those sums. So the first one says that I have 2 that have degree 1. So there's a couple of ways I'm going to show this. I could just write them out. 2 of them have degree 1. It says 3 of them have degree 2. So I have 3 2s. It says 1 of them has degree 3. 1 has degree 5. And 1 has degree 6. So you can write them out individually. You could write it out as multiplication factors, right? It says that 2 have degree 1. It says that 3 have degree 2. And it says I have 1 of degree 3, 5, and 6. So either of those perspectives works perfectly well. What do I get when I add them together, or multiply and add them together either way? What's my sum? $22. It's 22. So if the sum is 22, this means how many edges do I have? Yeah, I have 11. So my edges are 11. Because 11 times 2 is 22. Okay, is that all right? Okay, we're going to talk about how we get from one point to another point. And there are 3 different descriptions in this section for doing so. The first description is simply a walk. A walk is a sequence of vertices, each linked to the next by an edge. So, for example, if you woke up this morning and let's say you live on campus and you're talking about your daily routine. Okay, so you go from your dorm and you come to my class, and then you go from my class and you go over to the GC to eat lunch, and then you go from the GC and you go over to Bailey Business Building. The walk that you took was from your dorm room to Bailey Business Building, and you're connecting each of those pieces with an edge. That's a walk. It just means you didn't have to get off the sidewalk to do it. That's really what it means. A path specifically is a walk that uses no edge more than once. So technically a walk, the original one, the walk, could mean you go from your dorm room and you come to Shawnee Hall, and then you go to the GC, and then you come back to Shawnee Hall. You repeat that direction, right, that path. And then from Shawnee Hall, you go over to Bailey Business Building, and that would be a walk because you repeated something. But it wouldn't be a path because you repeated the piece, the edge, that took you between the GC and Shawnee Hall. Are you with me? But the first description that I gave, where you didn't come back to Shawnee Hall and you went straight from the GC to Bailey, right? That would be a path instead, because I didn't cross any of the edges twice. So a path simply is a walk that does not pass over an edge twice. And then a circuit is a path that begins and ends at the same vertex. You do this all the time, right? Now specifically though, it's a path, not just a walk. So some of our circuits, some of our loops that we do are not circuits, right? So again, my example, if you had gone back and forth between the GC and then you went back to your dorm room or something like that, that wouldn't necessarily be a circuit. But if you start and end at the same spot and you don't cross over any of those sidewalks, those edges twice, then you would have a circuit. Okay? So there's slight differences in these descriptions. Just be careful when you're using them that you're doing what you intend to do. All right? Because we use these words in English, path, walk, all the time, and we don't necessarily mean this specific definition, right? So just be careful with that. All right, so here's an example. We're going to use this graph and we're going to decide if we have a walk, a path, or a circuit. It is possible to have none of them. It is possible to have all of them. Or it's possible to have maybe a couple of them and missing a third kind of thing. We can do that too, or one of them missing the other two. So we really do have to check every single piece individually to see if it works. Okay? So the first picture, the first part A that we have for our picture. Okay, let me copy this and paste it down here. Asks us if this A to B to E is a path, is it a walk, is it a circuit? Okay, so let's look at this actually by doing some coloring on our map again, okay, or on our graph again. So we have A to B, and then we have B to E, and then we have E to C, okay, in the yellow. In order to be a walk, it means I was actually able to draw that in and stay on the edges. Was I able to do that?
Where are you getting
Oh. Sorry, that's the part I didn't want. I wanted to continue on. Sorry, you're fine. A to B, B to E. Thank you. All right, A to B, B to E. Was I able to draw it and stay on the edges? Yes, okay. Notice, if this had said A to B to C, it wouldn't have worked, right? So just because they put the 3 things in a row, that doesn't mean that they're going to work. We actually have to see if the edges connect the way that it's described. And this one does. So it is, in fact, a walk. The walk simply means I can do that and stay on the edges. Is it a path? Well, path means it's a walk. I determined it was a walk, so I'm halfway there. And it means that it didn't repeat any edges. Did I repeat any edges? No. So this one's a path as well. Is it a circuit? No. What would I have to do in order for it to be a circuit? Yeah, it needs to go back to A. So if I've got this already set up and I put an arrow A at the end, then I would have a circuit. But it doesn't end at the same place it starts, so I do not have a circuit. I just have a walk and a path. Okay, everybody good? Okay, we're going to change color so that I can use the graph still. I'm going to use orange. All right, we've got D to C to E to B to D to A to E to C. Yeah, it's crazy. We're just going to find out what happens. Okay, so we're just going to trace it. And if we run into the ability to not trace, then we stop and we can't do anything else, right? So I just want to see, first of all, can I trace the description? So this says D to C, and then C to E to B, B to D, D to A to E, and E to C. Was I able to trace through all those pieces? I was, which makes it a walk. This is a walk. But is it a path? No. Why does it fail? Yeah, there's a place where I have E to C as well as a place where I had C to E. I repeated this edge, right? So I don't have a path. Do I have a circuit? No. But I started and ended at the same point. But a circuit has to be a path. So in the very nature of the way this is described, I can't jump from walk to circuit and not go through a path. Has to be a path. So the fact that I don't have a path here means I don't have a circuit either. So this one is just a walk. All right. A complete graph. A complete graph is a graph in which there is exactly one edge going from each vertex to each other vertex. It's got the most edges possible. That's what it really says. Every two vertices is connected with an edge. We think about this in terms of like algebra stuff all the time. You remember the phrase that says every 2 points are connected by a line, right? Or there's a line that's exactly one line between every 2 points, right? Like you can draw it. It's that kind of an idea. Okay, but here, like, it actually exists. It has to actually be connecting, like you can see those lines in there, those edges in there. So our example, number 7, gives us a picture. I've got A, B, C, D, E, and F, and I want to know, is this a complete graph? Notice it does not have a dot in the middle. That doesn't change my answer actually here, but just be aware of the fact that it's the overlaying pieces, but it doesn't have a dot in the middle. Is it complete?
There's more than one edge coming from each vertex. Does that make it not complete?
That's not a problem. I can have more than one edge coming from the vertex. My question I'm trying to answer is if I take any two vertices, is there an edge connecting them?
Oh, okay.
No. Why not, Jonathan?
Because you can't directly connect A to C.
A to C. Okay, so that's an example of one. A and C are not connected with an edge. Are they connected with a path? Yeah, so it makes it a connected graph, but it's not a complete graph. It's connected, I can get there, but I can't get there straight shot, right? I have to go through some other point in order for that to happen, some other vertex. So this one's not complete, and in fact, it fails in several places, so it's not complete. That was right. We do not have an edge A that goes to C. This does not happen. Right? What else do we not have? Throw me out some other things. A to E doesn't happen. Any others?
B to D.
Yeah, B to D. Yeah, so there's a lot of them, right? How many do I need for it to fail? Just one. What was the other one we said? C to D? E? Okay. Yeah, so we've listed several. We really only need to care that there's one. As soon as we find one that doesn't work, it fails to be complete. This one is not a complete graph. All right, there's a definition piece that I'm going to introduce, not because you're going to have to deal with it directly, but because every now and then it shows up in directions of something, and I just want you to make sure you know what it's referring to if you see it. It's subgraph. A subgraph is simply a graph that includes some of the original vertices and all of the edges that connected them originally. So you can remove some of the vertices and edges, but if you keep the vertices, all the edges that were there connecting them to start with have to still be there and connected. And I'm going to go back and get one of my pictures and copy it over here. This is a good one. All right. We had that picture before. This is the whole graph. If I were to keep the vertices A, B, D, and E, and I were to take off this piece, this would be a subgraph. I kept all the original vertices, right? Well, I mean, I kept the vertices that I kept, and I kept the original lines or edges that connected them. So at the point when I deleted point C, I only deleted the edges that came from C out. Every other edge that went between the 4 points that I kept are still there. That's called a subgraph. It's a portion of the graph that we can talk about eliminating one of the vertices and any of the edges connecting them. Coloring. A coloring is an assignment of a color to a vertex in such a way that the vertices joined by an edge have a different color. And the smallest number of colors needed is called the chromatic number. So imagine if you looked at the United States map. You've seen the United States map before where they've colored in states, correct? And usually it's not just like there's 50 different colors that they use, right? They repeat some of the colors. But they do try to avoid what happening? The same colors right next to each other. So this is an application of this process right here. They're typically trying, especially with publishing the way that it used to have been done when maps would have first happened and colors would have been first available, they're typically trying to minimize the number of colors because every color you add to something costs extra money. Okay? I was a yearbook editor in high school, and we would add color to pages. Yearbooks now are just all in color. You're welcome. It didn't happen back in the day. Every time you added a color, it added a cost. And so we had to minimize the colors, but we could like do variations of them, right? Like we could make it, you know, on a scale. Like you used pink, but you could use dark pink to light pink as long as you like the percentage was the same color. You could do that, but that's the most you could do and still stick with the same one color. And every color costs extra money. Same thing with the maps. You're minimizing the color on the maps because there's a cost involved. Okay? So when we're looking at this, that's the idea in mind. We want to use as few colors as possible, and that number that's the fewest number is called the chromatic number. All right, so coloring a graph, this is an abbreviation of some of the notes inside of your book, if you were to go back and look, or the notes inside of my math lab. But this is the basic idea of how we color a graph. You choose a vertex with the biggest degree, and it says a vertex, because you might have many of them that have all the same biggest degree. Just pick one. And you use the same color to color as many vertices as you can without coloring adjacent vertices. I haven't actually defined adjacent vertices, but they're exactly like what you would think. Adjacent means right next to, right? Your adjacent, you know, the dorm room adjacent to yours is the one that's right your next door neighbor, exactly your next door neighbor. So adjacent would mean in that context you probably share a wall. Here you share an edge. Okay? So you're trying to color as many other vertices as you can with that color in such a way that the two that you're coloring are not next to each other like the states. Okay? After you've done all the coloring you can with that color, say it's yellow or whatever, You choose a new color. And you choose one of the things that are not currently colored of biggest degree, and you repeat. Like the shampoo bottle, right? Wash, rinse, repeat. Repeat. And you repeat until you have colored every vertice. You ready to try one? Okay. This is similar picture to what we had a moment ago. How is it different than the last picture I drew? There is a point this time in the middle, right? There's a vertex that's actually in the middle. Okay, so take a look. Looking at that list of instructions, it starts out by saying I want to pick the point with the biggest degree. What point here has the biggest degree? G. You're right. G is my biggest degree. So I'm going to color G, whatever color you pick, I'm going to use yellow. Okay. I don't put the yellow away until I make a decision. Can I color any other point yellow? No. Why not? Yeah, there is an edge from G to every single other point. If there weren't, I'd color that other point yellow too. But at this point, I can't color anything else yellow because every point is adjacent to G. So change colors. I'll go to green. Look at all the rest of the points. What can you tell me about their degree? They're equal. It's all three. So it doesn't matter which one you pick, just pick one of them. I'll pick A. It's alphabetical, right? So there's A. What other points could I color green potentially if I've colored A? C and E. I technically could color D as well. I just can't color all three of them, right? Okay, so any of these three potentially could be colored in green, but I'm trying to use as minimum number of colors as I can, so I want to color as many of them as I can green, which means I'm going to color C and E. So E, C, or green. And I change color. We'll go red. I pick another one that's not been colored. I'll color F. Now what? Yeah, the other two actually can also be colored that same red, right? So, what is my chromatic number here? It's 3. It's the number of colors I needed. The minimum number. Could I have colored it with more colors? Sure. But the goal was to try to minimize the number of colors. So the chromatic number here is 3. Okay. So I wanted to show you an example of how graph theory can be used. We've seen an example similar to this before in another context, but this is kind of a funny one that shows up in your in the My Math Lab or the book portion of this. It's a party. So at a party, there are 4 males and 5 females. I think that somebody's date stood them up. That's what I think happened, but we're just going to go with it. 4 males, 5 females. During the party, each male danced with each female, and no female or male pair danced together. Okay, we need to know those details or we won't be able to draw the picture properly. It says, draw a graph with vertices representing the people at the party and edges showing the relationship danced with. Okay, so the edges are talking about a specific kind of a description that connects people. Right? We can use, I keep talking about sidewalks and streets and things like that. That's fine because you have a very good picture in your mind, but it doesn't have to be a physical object. It can be a descriptive object here, like it is, okay? Danced with. So we're going to draw a picture and we're going to figure out how many edges that there are in the graph. All right, so in order to kind of keep our pieces clear, we're going to make our vertices each of our people, and it will help us if we put all the men on one side and all the women on the other side. Does that make sense? right? Organizing our data. So I'm supposed to have, oh, I need a bigger stroke. What's this one? I'm supposed to have 4 gentlemen. And if you want to label that so you can remind yourself of what you're doing for your dots, these are our men over here. And then I'm supposed to have 5 ladies on the other side. There's 5. So these are our women. Okay. And we're supposed to draw edges that connect the men to the women, and no women to women or men to men, because that's the description I was given, right? And we're supposed to draw these edges for every single pairing. So gentleman number 1 comes in, and he's going to get to dance with every single woman on the right. So we've got one here, one here, one here, one here, and one here. Right? What do I do for gentleman number 2? The same thing, right? So gentleman number 2 has the same 5 dances that he gets to have with each of our ladies. And gentleman 3. We're assuming they're all gentlemen. They're nice, right? Not ornery. Okay. And 4. What a fun graph. What fun. I don't believe that we actually get to this description, but just so you know, this actually has a name. It's called a bigraph. If I were to put all of the men in one category, all the women in the other category, there's no connection between the men and the men and between the women and the women. So when you have the ability to do that with your vertices, it's called a bigraph. The question, though, back to our question. This is our graph. The question asks, how many edges are there in the graph? 20. How'd you get 20 so fast, Aaron? Okay, so each of the, I'm going to label it out a little bit better, more detailed. Each of these men have 5 dances, right? And if we were to add them all together, there'd be 20. I could do the same thing over here with the ladies. Each of the ladies doesn't have 5 dances, they have 4. Because somebody didn't come. So there's 20. So there are 20 edges, no matter which of these categories you count. Don't count them both, right? Don't count them both. But the sum of degrees would be 40, if that's what we were asked to count. If you literally want to count just the edges, which is what we're asked to find, are actually 20. Is that all right?